In this video, you will learn to recognize and use the terms translation, rotation, reflection, pre-image, image, mapping, one-to-one mapping, transformation, isometry, and congruence mapping. So basically a bunch of definitions and terms, and then we also have a little bit of math in here as well. So to begin, we want to discuss the term mapping. All right, so what is a mapping? Well, mapping is when you can take each point on a pre-image and it corresponds to a single point on an image. So a pre-image is like the original object or the original image. So let's say here we have a triangle and this is like point A, B, and C. This would be like your pre-image. And then if we can map it over here such that we have another triangle like this, and we can have this A prime, B prime, and C prime, this would be a mapping because we're mapping each point from this pre-image, this original shape, and we match it over here, or map it over here, to corresponding points on this shape. So this is one example of a mapping. And this term can be used interchangeably with the word function. So in algebra, we use the word function to show a mapping of different numbers, and a mapping is maybe more specifically geared towards geometry. So mapping is more like a geometry term, function is more of an algebra term, but they're used interchangeably because they really have the same idea behind it. And a function is where each number in the first set corresponds to a single number in the second set. Just like a mapping has each point in the first set corresponds to a point in the second set, a function is a number that does the same thing. So you see the similarity between mapping and function. Now as far as the notation of a mapping, here is mapping notation where it looks kind of weird at first. We have the letter and then a colon. All right, what this does is it names the function or the mapping. Remember, we can use those terms pretty much interchangeably. So this would be our mapping. So this, we name it mapping f or function f. And this function maps the letter x right here, maps it over to its square. All right, so that's what this notation means. And we can have the same scenario represented with function notation because again, mappings and functions are pretty much the same thing. In function notation, we can write this as f of x equals x squared. So again, the same idea between these two notations, between mappings and functions. And what this would look like is, let's say we took the number 4, for example. This was our pre-image or our input. If you put a 4 in to this function, it's going to map it to its square. So you square 4 to get 4 squared, or 16. And then in algebra, we would write this as an ordered pair. X is 4, y is 16. Your input is 4, you get out a 16. Or we could say your pre-image, your original number is 4, and then your image would be 16. So again, all these terms can be used interchangeably. Now, dealing with functions, we have what's called a one-to-one function. Or again, we can replace the word function with mapping. So one-to-one mapping or function, it's really the same thing. And what this is it's a function or mapping where each number in the second set corresponds to a single number in the first set. So it's kind of like our definition of function, but backwards, right? Because a function, by definition, has each x value paired with only one y value. Right? That's your definition of function. Now, a one-to-one function, if something is one-to-one, each y value must also correspond to only one x value. Or in other words, each output must only correspond to one input. Or another way of saying that again would be each image would correspond with only one pre-image. So what does this look like? Well, it might make more sense to illustrate this with an example of what is not a one-to-one function. So here we have an example of something that's not one-to-one. we have here a function, the same function actually that we had before. This is function f, where it maps x to x squared. And this is not one-to-one because if we plug in, let's say, a 3 for x, if x is 3, x squared would be 3 squared, or 9, right? So the 3 pairs up with the 9. This is your pre-image, 9 is your image. 3 is your x value, 9 is your y value. All right, so the 3 maps with the 9. But if we put in a -3 for x, let's say x is -3, then we have -3 squared, which would also be 9. So because this y value, this image, corresponds with more than one x value, or more than one pre-image, that means that this is not one-to-one, because the 9 matches back with a 3 and a -3. It is a function because each x value is only paired with one y value. Right? You plug a 3 in for x, you only get one answer back out for y. But if you put in a 9 for y, we get two different numbers possible for x. All right, so this is not one-to-one. Now, all this terminology may be a little bit abstract for you, and it may be difficult to fully understand what everything means. So we're going to take a look at a couple examples to kind of solidify in your mind what these different terms mean and what it looks like in context. So here's example 1. We are told that function h maps every number to a number that is 4 more than 3 times the number. So our first question is going to be, can we express this fact using function notation? All right, so using function notation. So this one, okay, function h, with function notation, we can write that function as h of x. Okay, that's function notation. And it maps every number, so it's equal to, where every number is being mapped to a number that is 4 more than 3 times the number. So 3 times the number would be 3 times x, and then 4 more than that would be plus 4. All right, so this would be your function h represented in function notation. And then if you were told to put this in mapping notation, it would be the same idea, where you'd have the letter h and then colon, so that represents function or mapping h. And then we're mapping the letter x with 3 times x plus 4. So that would be mapping notation right there. And actually in the notes, we want this, our actual question we wanted was mapping notation. So we're going to see that here on the next part. It's actually put in mapping notation as opposed to function. It's supposed to be mapping. All right, then our second question is, using this mapping that we have, can we find the image of 5? So what is the image of 5? So in other words, the 5 is what we're plugging in, and we want to see what do we get out. So the word image, you can almost think of output. What is the output, or what is the y value? So what we do is we plug this in for x and see what is our output. What do we get back out? So you plug a 5 in for x and see what happens. So we have 3 times 5 plus 4, which gives you 15 plus 4, which is 19. So the answer would be 19 for the image of 5. Now question 3 is working backwards and is asking to find the pre-image of 10. So to do this, okay, we're trying to figure out what is our input, or what is our x value. So 10 is going to be what we get when you plug in something for x right here. So if this is your input, 10 is your image, which means you get that back out. That's your output. So what we have is a little equation of 3x plus 4 equals 10, and you need to solve this to find the pre-image, figure out what is x. So we can subtract 4 from both sides. We get 3x equals 6, and divide by 3, so x would equal 2. So the pre-image of 10 would be 2. And again, we find that by solving 3x plus 4 equals 10. So this example here is more dealing with algebra. We want to be able to use this in geometry context as well. So our next example is dealing more with a geometry type question where you are told that mapping F maps each point xy to the other point 3x comma y plus 1. So our first question is, can we express this using mapping notation? Now this one is going to look maybe a little bit different, but it's still the same concept where you have your mapping F. So we'll write that as a capital F and then a colon. So that's how we name our mapping. And what are we mapping? Well, we're mapping the point xy. So we'll write xy, that point. We're mapping that, so we draw an arrow, mapping it to the point 3x comma y plus 1. All right, and that's your mapping written in mapping notation like that. All right, so it's still the same idea as the other example, but it looks a little different because now we have a point as opposed to just a number. Now from here, our second question is we want to find P prime and Q prime, which are the images of points P and Q. All right, so to do this, okay, we have points P and Q. Those are our pre-images. So that is what we're plugging in here into our pre-image. We're trying to see what do we get back out. All right, so for 2, 1, for example, for right there, we want to plug in a 2 and a 1 and for x and y. What do we get back out? Well, 3 times 2 is 6. And then y plus 1, we do 1 plus 1, which gives you 2. So P prime would be the point 6 comma 2. And then Q prime, we do the same thing. So we plug in this point, negative 3, 0, in place of x and y. So we have negative 3, 0 is what we're plugging in. It's kind of a messy negative 3. But you plug negative 3 in for x, so you get 3 times negative 3, which is negative 9. And then you plug a 0 in for y to get 0 plus 1, which is 1. So Q prime would be the point negative 9, comma 1. So that's how you find the image of points P and point Q. So we've kind of transitioned our mappings from just numbers, like in algebra context, and we are transitioning and using these now in geometry context. All right, and in geometry, there's different types of mappings that we have. Okay, we have maybe a translation or a rotation or reflection or dilation. And with these different mappings that we have what's called an isometry. So it's a specific type of mapping. Now what this is, by definition, if you take the word isometry, so you have the prefix iso, I-S-O, that means equal. So like isosceles triangle, okay, it's got the prefix iso, and isosceles triangle means we have two sides that are the same or equal measure. So that prefix iso we've seen before in geometry, and here again it means equal. And then the other part of the word, the part that says metry, M-E-T-R-Y, that means measure. So like geometry is the measure of geo, which is the earth. So it's like earth measure. All right, so isometry literally means equal measure. So if you understand what the word means, if you break it apart piece by piece, that gives you our definition. Because what an isometry is it's a transformation that maps every segment to an equal or congruent segment. All right, so it's creating equal measure of segments. All right, so that's your definition, and a description of this is it preserves distance, so it preserves the length or distance of a segment, and it's also called congruence mapping for that reason, because it's creating congruent parts, congruent segments. All right, and then also if that's the case, if it's creating congruent parts, the pre-image, so the original input, and the image, the output, are going to be congruent. So with isometries, there's a theorem that is important to know, and that is dealing with triangles. So this theorem says that an isometry maps a triangle to a congruent triangle. All right, so we can do kind of a formal proof to verify this to be true. So our given information is we have isometry T, where we are mapping this triangle ABC to triangle A prime, B prime, C prime. And we're trying to prove that triangle ABC is congruent to triangle A prime, B prime, C prime. So what does this look like? Well, here's a picture. So we have triangle ABC, and we are mapping with these red lines. We're mapping each point to a corresponding point over here on this triangle. And we're trying to prove that this triangle ABC is congruent to the triangle A prime, B prime, C prime. And this is actually very quick to prove because we use our given information, our original statement. So the isometry right here, by definition, by that original statement, we know that we have congruent parts. Right? That's your definition of isometry, right? Isometry means congruent parts. So we know that A prime is congruent to A prime, B prime. We know that AC is congruent to A prime, C prime. And then BC is congruent to B prime, C prime. And the reason is because that's your definition of isometry. That's what it means. So look what we have. We have two triangles that have three sides congruent. And we've learned in our chapter on triangles that if we have three sides congruent, then we have congruent triangles because of our side, side, side postulate. All right, and the proof's done. We just verified that indeed, with an isometry, the triangle is being mapped is going to be mapped to a congruent triangle. And we really can extrapolate this to any polygon, really, where we're going to have congruent side lengths, which will in turn create congruent polygons. So with this information, we have two corollaries. The first is that an isometry maps an angle to a congruent angle. All right, for that same logic that we just had with those triangles, right? If we have congruent triangles, then all the angles are the same as well within that triangle. So the congruent triangle also implies we have congruent angles as well. And then corollary 2 kind of goes along with what I said with the fact that the isometry not only works for triangles, but also for any polygon. So if it's creating congruent polygons, that means the areas will be the same because we have congruent shapes. And that's what corollary 2 says. So it says an isometry maps a polygon to a polygon with the same area. All right, so we've dealt with mappings. We've dealt with a specific type of mapping called an isometry, where it preserves the distance or the shape, the size of the object. Now we have different types of mappings still, different types of transformations, as we call them. And there's four main types we're going to discuss in this particular chapter. So we have what's called a translation, we have a rotation, we have a reflection, and we have a dilation. Now these are all mappings, but not all of them will be isometries. Okay, we'll just kind of give an overview of what each of these are, and then in the following lessons we will go into more detail with these different transformations. So the first one is a translation, so make sure you know what this is. And what the translation is it's a sliding or moving of an object. So what we're doing is we're just changing the location of the object. So if we're just moving the location, we're not changing the size of the shape at all. This would be an isometry because isometry keeps the shape and keeps the size the same. Now what does this look like? Well, right here, if we took this shape, and this would be our pre-image, and moved it over here to this location, okay, that would be your image, that's your output. That would be a translation. We can move it, all right? And then here's another picture. This is our pre-image. We can move it up in this direction if we wanted, and this still would be a translation, even though it's not left to right. We can move it any direction, and we still would have a translation. All right, so this would be our pre-image, and then where it ends up, that's going to be your image. So we have translations. Next we have rotations. Rotation is the rotating or turning of an object. And with a rotation, okay, this can change both the location and position of an object. All right, so we can move the figure either clockwise or counterclockwise around a point, a particular amount. So we can rotate it, a fraction of a turn or a certain number of degrees, like maybe 180 degrees or 90 degrees. And with the rotation, we're not changing the shape of the object. We're just changing, the orientation of it, how it's being positioned in space. So because the original shape is going to be the same as the output shape, the pre-image is the same as the image, this would be considered also as an isometry because it's preserving distance or the lengths of the sides. Now an example of this would be right here, where if this was your pre-image and you rotate it about this point, let's say we do it clockwise like this would be your image. And this rotation, we've turned it 90 degrees or a quarter of a turn. We can take the same shape and turn it different amounts. So we can turn it around this point, maybe 180 degrees to get this image right here. Or we can turn it further, another quarter turn to get this new image. So turn it like this to get this new image right here. And again, that's a rotation. We've turned it 270 degrees, which is 3/4 of a turn. So with rotations, we can rotate at different amounts around a particular point, and it could be clockwise or it could be counterclockwise. The next transformation we have is a reflection, and this is the idea of looking or creating a mirror reflection or a mirror image of something. So if you look into a mirror, you see your reflection, right? So that's the idea. And what this does is it flips a figure across some sort of line of reflection. So if you're looking in the mirror is your line of reflection. And again, what this does is it creates a mirror image of the original object. And more specifically, every point on the image is the same distance from the line of reflection as its corresponding point on the pre-image. All right, so we'll see an example of that here in a moment. And with this, we are preserving distance. It's not changing the shape or the size of the object. So this would still be an isometry because it's preserving distance. So here's an example. Here's our pre-image. It's a picture of a heart. And let's say this yellow line is our line of reflection. Okay, our image would be reflected across that line such that each point is the same distance from the line of reflection as its corresponding point. So if you were to look at this point right here and its corresponding point right here, okay, the tip of the heart, that distance from the line of reflection is going to be the same. And if you take any point, let's say right here, that point and its corresponding point down here, the distance to the line of reflection would be the same for both of those points. All right, so that is the idea behind a reflection. And again, we see here another picture. Here's a quadrilateral. That's our pre-image, and we can reflect it across this line of reflection to get a mirror image on this side. All right, so make sure you know those three terms. We have translation, we have rotation, we have reflection. And the fourth and final transformation we'll discuss in this lesson is what's called a dilation. All right, so a dilation is when you take a shape and you either increase it in size or decrease it in size. So it's creating a similar shape. So for example, right here, we see this original triangle, ABC. If you take a point, like right here, and construct these rays going through each vertex like this, we can construct our similar shape in this manner, where you take each point and put it on these rays that we have created. All right, so like if you measure the distance from O to B, for example, O to B, that length, and then looks like here we're about doubling it, so let's say we double that length, that would give you this point over here. And then if you measure the length from O to A, okay, we have to double that distance to get this new point over here, A prime. And again, O to C, if we double that, we're going to get this point over here, C prime. And we connect those three dots and we get this similar shape. All right, so basically if you ever see something like this where the shape is still maintaining the same shape but is creating different size of the shape, so either bigger or smaller, this would be a dilation. And with this, because it's not preserving the size, this would not be an isometry. Because an isometry, by definition, needs to keep or maintain congruent side lengths. So in this lesson, we've learned about mappings and functions. We've learned about different types of transformations. We've learned about isometries. And in the following lessons, we'll go into more detail with those different types of transformations. And that concludes our lesson for today. We will see you next time.